Comparison test for series. Let's firstly make a few remarks about positive term series. Recall that if we have positive term series, that is, n is positive when n is bigger or equal than 1, then if the series is divergent, then it diverges to positive infinity. So if positive term series is divergent, then it diverges positively. That's the first command. Second command is just in general. If you look at the two series, and the difference between the two series is, first series we start adding with n equals to 1, second one we start adding with capital N. And if we're concerned about convergence or divergence of a series, so we can concern about the question whenever a series converges or divergent, then if you look at the first series, that is a1 plus a2 plus a capital N minus 1 plus a capital N plus and so on. What you notice is that is the series where we start at n capital N and n plus that initial part. So if we are concerned about the convergence or divergence of a series, what we notice is the series where we start at n equals to 1 and the series when we start at capital N, the difference is going to be that initial part, which is finite, let's call it capital A. So if we're concerned about the question whenever a series is convergent or divergent, these two series are going to be essentially doing the same thing. They both converge or diverge. Both are convergent or both divergent. Let's look at the two positive term series. Positive term series, which means these guys are positive. And let's say that Bn is bigger or equal than a. So a term in the second series is bigger. Then let's have a look and let's consider two situations. The first situation, if we have a smaller series is divergent. If smaller series is divergent, what we can say about the bigger series? Then the bigger series will, let's look again, n is less or equal than bn. Therefore, if we add up bigger numbers, we should get bigger series. Now what we have here is this one is divergent because it's positive term series. It diverges to infinity, so it equals to infinity. So we conclude that the bigger series bigger or equal to infinity, so it better be equal to infinity. So the bigger series also should be equal to infinity. divergent. So if smaller series is divergent, then the bigger series is divergent. That's the first situation. Second case, if we start with bigger series convergent, then let's have a look. Then we have an less or equal than bn, add them up, we should get something which is smaller, and therefore this is convergent. This series is convergent, so it's finite number. So we conclude that this guy cannot be equal to infinity, and because it cannot be equal to infinity, it cannot diverge. So it cannot diverge. It cannot diverge, so it better be convergent. So our conclusion is, if bigger series is convergent, then a smaller series is convergent too. So conclusion was is convergent. Now I will write our findings as a comparison test. I'm going to write CT for comparison test most of the time. So comparison test state the following. Let AN and BN be two series such that for all n both series are positive, have positive terms, and the terms of a second series are bigger or equal than terms of the first one. So terms of second, then we have two conclusions, possibilities, two cases, as we did in the previous case. If smaller series is divergent, then the bigger series is divergent. Second, if bigger series is convergent, then smaller series is convergent. So we have two cases. So comparison test tells us if we have two series and we have one series is bigger than another series, then if smaller series equals to infinity divergent, then the bigger series divergent. If your bigger series is convergent, then your smaller series has to be convergent. And comment. If in the previous series setting, then we have two series and we have bigger series. Now we did case 1 and 2, case 3, if our bigger series is divergent, then we cannot say anything about smaller series, because our smaller series can be either finite number or infinity. It's difficult to say. In case 4, if we have our smaller series is convergent, that means smaller series is finite number. If we have finite number for smaller series, then our bigger series possibly can be finite number or still be infinity. Then we cannot say anything about the series over here. That's the first one. Let's run an example on 2 on comparison test. Determine if the series 1 over n squared plus 1 and from 1 to infinity is convergent slash divergent. What we notice is 1 over n squared plus 1 and 1 over n squared. N squared plus 1 is bigger than 1 squared, so denominator in the first one is bigger than in the denominator of the second one, so fraction is going to be smaller. Now if we look at the series 1 over n squared plus 1, it's going to be less or equal than 1 series of 1 over n squared, and from 1 to infinity, and from 1 to infinity. The series here is, we recognize that as a p series, p equals to 2p bigger than 1, convergent. It is convergent by p-test, p-series test. So now we turn around and we conclude that our original series 1 over n squared plus 1 is convergent by comparison test, because our original series is less than something which is convergent, less than a finite number, so it should better be convergent by CT. When using comparison test, we're often going to use the following information for big, huge n. The following will be true. If you want to compare natural log of n, the natural log is always smaller than a polynomial, less than n. Natural log actually going to be smaller than a square root of n. It's going to be smaller than actually n to any power as long as that power is positive. And also, if you want to compare and use comparison test with something which involves exponential function, for example e to n, and e to n is actually opposite of natural log. It's big, so it's bigger than polynomial. Actually, it's bigger than any polynomial. It's bigger than n squared, and so on. It's bigger than e to n is bigger than n to a, where a is any positive number. So in general, if you're talking about exponential growth, then b to n is bigger than n to a, where we want to have exponential growth here, so b is bigger than 1 and a is positive. Again, that situation holds when we are talking about huge big n, starting with like 1,000, 10,000. Next example, we want to determine whenever the series 1 over ln n, and starts at 2 to infinity, if it is convergent or divergent. So we want to figure out that piece of information. So what we do is we recall that natural log of n is going to be bigger when n is big, and say when n is bigger than or equal than some letter n. Right. Now if I take and divide by these expressions, if I divide by a bigger number, I'm going to get smaller fraction, so I'm going to get it this way. So we're going to get summation now, and from capital N to infinity, and from capital N to infinity, and we kind of keep the same sign. We recognize the series on the right, that is harmonic series. Harmonic series is divergent. Therefore, we turn around and we conclude that that series on the left side, which is supposed to be bigger than harmonic series, is divergent to by comparison test, because harmonic series diverges to plus infinity, and it doesn't matter where we start. So we conclude when we start at 2 is divergent. Next example, we still want to determine whenever series diverges or converges, and we want to look at the series 1 over, let's say, n over e to n, and from 1 to infinity. E to n is bigger than n, say, to the 10, when n is big, and say when n is bigger than capital, big or equal. Thus, 1 over e to n and 1 over n to the 10, if you divide by a bigger number, we're going to get smaller fraction. So multiply both sides by n. We're going to get the expression which looks like this. So we conclude, if we switch to series, with this series to the left, n over e to n supposed to be less or equal than series. We reduce that expression 1 over n to the 9, starting with capital N. We recognize this series, that is p series, p equals to 9, bigger than 1, convergent by p-test. So we turn around and we conclude that our series on the left, because it's smaller than something which is convergent, smaller than something that converges smaller than a finite number, is supposed to be finite number 2. Convergent 2. And therefore our original series is convergent. One more example. Still concerned about question about whenever series converges and divergence, and we want to look at the series 1 over n ln n, say n starts from 2 to infinity. ln of n is less than n, so n ln of n is less than n squared. So now I'm going to divide. So I'm dividing by bigger number, I'm going to get smaller fraction. Okay. So again, for big, huge n, ln is less than n. So we got one series of 1 over n ln of n is bigger than or equal than series of 1 over n squared. We recognize this series, that is p series p equals to 2 bigger than 1 convergent. Therefore we turn around and we say the series to the left is, it's bigger than convergent, it's bigger than finite number, and actually that means we have problem because we cannot figure out what is going on here. So comparison test doesn't tell us what is going on if we are bigger than convergent series. What we have to do is So we have to use the integral test. Test here to show that our original series is divergent. So we cannot apply a comparison test to this one.